Welcome to the Efficiency Quest, your strategic guide to mastering data structures. Every line of code that stores data is a decision point, one that can make your application lightning fast or painfully slow. In this video, we'll embark on a journey through the evolution of data structures, exploring how each one addresses the limitations of its predecessor. From the basics of arrays to the sophistication of self-balancing trees and specialized tools like the Fenwick tree, you'll gain a clear understanding of when and why to use each structure. Let's begin our quest for efficiency and discover the logic that powers high-performance software. Start with the foundation, arrays. Arrays store elements in a contiguous block of memory, which means you can access any element instantly using its index. This direct access is incredibly fast and efficient, making arrays ideal for situations where you need to frequently read data at known positions. However, arrays come with some trade-offs. They have a fixed size in their static form and require all elements to be of the same type. While they're cache-friendly due to their memory layout, making changes like inserting or deleting elements can be costly, especially if you need to shift many elements. When it comes to performance, arrays shine in some areas but struggle in others. Accessing an element is a breeze, just one time, meaning it's as fast as it gets. But searching for a specific value can be slow, often requiring you to scan the entire array, which is n time. Inserting or deleting elements, especially in the middle or at the beginning, is also because you have to shift all subsequent elements. This inflexibility makes arrays less suitable for dynamic datasets where frequent changes are expected. Arrays offer powerful random access, but their main weakness is the ripple effect caused by insertions and deletions. Any change, especially in the middle, can trigger a chain reaction, shifting all subsequent elements and making the operation expensive. This limitation becomes a significant bottleneck in applications that require frequent updates. As we seek more flexibility, it's clear that arrays, while foundational, aren't always the best fit for dynamic data scenarios. Overcome the rigidity of arrays, we turn to linked lists. Linked lists introduce flexibility by storing elements or nodes in non-contiguous memory. Each node points to the next, allowing for dynamic sizing and efficient insertions and deletions. Instead of shifting elements, you simply redirect pointers. This makes linked lists ideal for applications where data changes frequently. However, this flexibility comes at a cost. Direct access is lost, and finding a specific element requires traversing the list from the beginning. Linked list is made up of nodes, each containing data and a pointer to the next node. This structure allows for one insertion and deletion, provided you have a reference to the node. The list can grow or shrink as needed, making it highly adaptable. However, accessing an element by index is no longer instant. You must traverse the list from the head, which takes n time. This trade-off is important to consider when choosing the right data structure for your needs. Let's break down the performance of linked lists. Access and search operations are n, since you may need to traverse the entire list to find a value. However, insertions and deletions are one if you have a pointer to the node, making them much more efficient for dynamic updates. This makes linked lists a great choice for applications where changes are frequent, but random access is less important. Still, the loss of one access can be a significant drawback in some scenarios. A linked list solves the insertion and deletion bottleneck. They sacrifice fast access. This trade-off highlights a recurring theme in data structures. Improving one aspect often means compromising another. The quest for the best of both worlds, fast access and efficient updates, drives the evolution of more advanced structures. Next, we'll explore how hash tables attempt to achieve this balance. To the hash table, a data structure designed for speed. Hash tables use a hash function to compute an index from a key, enabling near-instantaneous data retrieval. This approach allows for one average time complexity for search, insertion, and deletion. However, hash tables are not without challenges. Collisions when two keys map to the same index must be handled using techniques like separate chaining or open addressing. Despite these challenges, hash tables are a cornerstone of efficient data storage. Hash tables excel in average case performance, offering one time for search, insertion, and deletion. However, in the worst case, such as when a poor hash function causes excessive collisions, performance can degrade to n. Fortunately, with a good hash function and proper implementation, these worst scenarios are rare. The main limitation of hash tables is their lack of order, making them unsuitable for tasks that require sorted data or finding minimum and maximum values efficiently. Hash tables deliver unbeatable speed, but they come at the cost of order. If your application needs to find the smallest or largest element or list items in sorted order, hash tables fall short. This limitation leads us to the next evolution in data structures, the binary search tree, which restores order while maintaining efficiency. Binary search tree, or BST, is a node-based structure that enforces a strict ordering property. For any node, all keys in its left subtree are smaller, and all keys in its right subtree are larger. This property enables efficient searching, insertion, and deletion, typically O log n in the average case. And in order, traversal of a BST visits all nodes in sorted order, making it ideal for applications that require ordered data and efficient updates. The average case, binary search trees offer O log n performance for search, insertion, and deletion. This efficiency comes from the tree's balanced structure, which keeps operations fast even as the dataset grows. Additionally, BSTs excel at finding minimum and maximum values as well as successors and predecessors. However, this performance is not guaranteed. If the tree becomes unbalanced, efficiency can quickly degrade. Efficiency of a BST depends entirely on its balance. If data is inserted in a sorted or nearly sorted order, the tree can become skewed, losing its logarithmic performance. In the worst case, a BST degenerates into a linked list with all operations degrading to n. This collapse highlights the importance of maintaining balance in tree-based structures. Skewed BSD, created by inserting nodes in ascending order, loses its core advantage. The tree's height grows linearly, and operations that should be fast become as slow as those in a linked list. This scenario is a performance catastrophe, emphasizing the need for self-balancing mechanisms to preserve efficiency. To guarantee efficient operations, we turn to AVL trees, a type of self-balancing binary search tree. AVL trees automatically maintain their balance, ensuring that the height of the tree remains O log n. This means that search, insertion, and deletion are always efficient, regardless of the order in which data is inserted. Core invariant of an AVL tree is the balance factor. For every node, the heights of its left and right subtrees must differ by no more than 1. If an insertion or deletion causes this balance to be violated, the tree performs rotations to restore equilibrium. This mechanism ensures that the tree remains balanced and operations stay efficient. AVL trees guarantee O log n performance for search, insertion, and deletion, even in the worst case. This reliability makes them a powerful choice for applications that require both order and dynamic updates. The cost of maintaining balance is minimal compared to the performance benefits gained. When an AVL tree becomes unbalanced, it identifies one of 4 imbalance cases and performs specific rotations to fix it. These rotations, right, left, left-right, and right-left, restore balance efficiently. Understanding these mechanics is key to appreciating how AVL trees maintain their performance guarantees. The left-left case occurs when a node's left subtree becomes too heavy. This imbalance is corrected with a single right rotation, which restores balance quickly and efficiently. Visualizing these rotations helps clarify how AVL trees maintain their structure. The right-right case is the mirror image of the left-left case. When a node's right subtree becomes too heavy, a single left rotation restores balance. These simple yet powerful operations are the foundation of AVL tree self-balancing. The left-right case is a bit more complex. It occurs when a node's left child has a heavy right subtree. This imbalance is corrected with a double rotation, first a left rotation on the left child, then a right rotation on the parent. This sequence efficiently restores balance. Similarly, the right-left case arises when a node's right child has a heavy left subtree. This is fixed by a right rotation on the right child, followed by a left rotation on the parent. These rotations ensure that the AVL tree remains balanced after every update. To truly understand AVL rotations, it helps to visualize the tree before and after each operation. These transformations show how balance is restored, keeping the tree's height optimal and operations efficient. Mastering these concepts is essential for anyone working with self-balancing trees. After performing the necessary rotations, the AVL tree regains its balance. The heights of the subtrees are within the allowed range, and all operations return to their efficient O log n time. This automatic rebalancing is what sets AVL trees apart from basic binary search trees. Let's look at another example of AVL rotations. By comparing the tree before and after the operation, you can see how the structure adapts to maintain balance. This adaptability is crucial for ensuring consistent performance, regardless of the order of insertions and deletions. After all necessary rotations, the AVL tree reaches its final balanced state. Every node satisfies the balance factor condition, and the tree is ready for efficient operations. This self-correcting behavior is what makes AVL trees a reliable choice for ordered, dynamic datasets. Sometimes, your application doesn't need to find arbitrary elements quickly, but instead must repeatedly access the highest or lowest priority item. This is where the heap data structure shines. Heaps are specialized, tree-based structures that efficiently support priority queue operations, making them essential for certain algorithms and simulations. Heap is typically implemented as a complete binary tree and comes in 2 main types, max heap and min heap. In a max heap, each parent node is greater than or equal to its children, so the root is always the maximum element. In a min heap, the root is always the minimum. This structure allows for efficient access to the highest or lowest priority item. Heaps offer O1 time for finding the max or min element and O log n time for insertion and extraction. These properties make heaps ideal for implementing priority queues, which are crucial in algorithms like Dijkstra's shortest path and event-driven simulations. However, heaps are not designed for fast arbitrary searches or maintaining full order. In practice, heaps are used whenever you need to repeatedly access the highest or lowest priority item. For example, they're essential in scheduling tasks, managing resources, and running simulations where priorities change dynamically. Their efficiency and simplicity make them a go-to tool for these specialized scenarios. For certain problems, even advanced structures like AVL trees and heaps aren't enough. Enter the Fenwick tree, also known as the binary index tree. This structure is designed for scenarios where you need to perform thousands of point updates and prefix some queries per second, such as in financial applications or real-time analytics. Fenwick tree addresses a specific challenge, efficiently supporting both point updates and prefix sum queries on an array. With a simple array, updates are fast but prefix sums are slow. With a prefix sum array, queries are fast but updates are slow. The Fenwick tree strikes a balance, enabling both operations in O log n time. Fenwick tree is stored in an array, but parent-child relationships are determined by bitwise operations on indices. The key concept is the least significant bit, LSB, which tells us the size of the range each node is responsible for. This clever use of bits allows the Fenwick tree to efficiently manage partial sums. Fenwick tree supports two main operations, query and update. To calculate a prefix sum, you repeatedly add values and move to the parent using the LSB. To update a value, you add the change and propagate it upwards. Both operations run in O log n time, making the Fenwick tree highly efficient for real-time data processing. Let's see the Fenwick tree in action. When you query for a prefix sum at a specific index, you traverse the tree by moving from the current index to its parent, accumulating values along the way. Updates work similarly, propagating changes to all affected nodes. This approach ensures both operations remain fast even as the dataset grows. For example, querying the prefix sum at index 13 involves traversing from 13 to 12 to 8, adding up the relevant values. This efficient traversal is made possible by the tree's implicit structure and clever use of bitwise operations. It's a powerful technique for high-frequency data updates and queries. Now that we've explored the major data structures, let's compare their strengths and weaknesses. Arrays offer fast access but slow updates. Linked lists excel at dynamic changes but lack fast access. Hash tables provide speed but no order. Trees balance order and efficiency, while heaps and Fenwick trees serve specialized needs. Understanding these trade-offs is key to making strategic decisions. Trade-off matrix summarizes the performance of each data structure across different operations. Arrays and linked lists are simple but limited. Hash tables are fast but unordered. BSDs and AVL trees offer order and efficiency, while heaps and Fenwick trees address specific problems. This matrix is a valuable reference for choosing the right tool for your application. Choosing the right data structure is a strategic decision. Consider your application's needs. Do you require fast access, frequent updates, ordered data, or specialized queries? Each structure excels in different scenarios. By understanding their trade-offs, you can select the most efficient tool and build high-performance software. Use arrays when you need fast, direct access to elements and your dataset doesn't change frequently. They're ideal for static data such as lookup tables or fixed-size buffers. However, avoid arrays for applications that require frequent insertions or deletions, as these operations can be costly. Linked lists are best for applications where data changes frequently and random access is less important. They're useful for implementing queues, stacks, and other dynamic collections. However, if you need to access elements by index often, consider other structures. Hash tables are perfect for scenarios where speed is critical and order doesn't matter. They're widely used for implementing dictionaries, caches, and sets. If your application requires ordered data or efficient min-max queries, look to tree-based structures instead. Use binary search trees and AVL trees when you need ordered data and efficient updates. They're ideal for databases, search engines, and applications that require sorted collections. Heaps are specialized for priority queues, making them essential for scheduling and resource management tasks. Fenwick trees are the go-to choice for applications that require frequent point updates and prefix sum queries, such as financial systems and real-time analytics. Their efficient O log n operations make them ideal for high-frequency data processing tasks. In summary, the journey through data structures is a quest for efficiency. Each structure offers unique strengths and trade-offs, and understanding these is key to building high-performance applications. By choosing the right tool for the job, you can ensure your software is both fast and scalable. Thank you for joining us on this strategic guide to data structures.